The solid lies between planes perpendicular to the x-axis at x equals 0 and x equals 4. The cross-sections are squares whose diagonals run from y equals negative square root of x to y equals the square root of x. In order to explain what this problem looks like a little bit better, I'm going to graph it. In the two-dimensional plane, we have the square root of x and the negative square root of x. And what I did here is I just took 2 points and put them in between each other so you can see where the cross-section would be. Now keep in mind the distance from this point to the x-axis is represented by the square root of x. Now if we graph this in 3 dimensions, we'll get a shape that looks like this. So keep in mind that the diagonals of the square were represented by the distance of the square root of x. So if this is the square root of x, then this is the square root of x, and then this is the square root of x. Now to make this a little easier to understand, let's pick an x value such as 2. So if I let a equal 2, or close to 2, then this distance right here, this black line right here, is square root of 2, which would make this distance the square root of 2, and so on. So this is what it looks like if a shape has the cross-sections that are perpendicular to the x-axis that are represented by the square root of x. This is also what it looks like if the diagonals are given by the function instead of just a square like in example 1. So if I animate this, we see how this moves across the x-axis and it creates a volume of a shape. So this is not made by this rotating around in a circle because it's just made by these square cross-sections going back and forth. So what this actually makes is more of like a tent type shape. Okay, if you were to look at it from the top, it would look more like a tent. So step 1 is to draw it on your paper. So take a second and draw that out. You typically want to draw it in the 3D plane, where our top function here is the square root of x, and this bottom function is negative square root of x. This axis that looks like it's going diagonal is our x-axis, and this axis right here is our y-axis. And do keep in mind that the diagonals here, if this value here is x, then this length right here is the square root of x, and the same for all of these. So step 2 is to determine the area of each cross-section. And so let's just go back to our geometry and let's remember that if this is a square, then we're going to get a 45, 45, 90 triangle, where if I let this sides equal s, then the hypotenuse is s square root of 2. Now let's apply that to our problem. So now what we're going to do is we're going to look at the square shape, but we're going to use our function instead of just s. So this is the square root of x, and this is the square root of x. And so in order to find this side we'll call y, we need to use the Pythagorean Theorem. So we get the square root of x squared plus the square root of x squared is equal to y squared. So this is x plus x equals y squared. So y is equal to 2x. And then you take the square root of both sides and you get y is the square root of 2x. So now that we know the side length of this, we'll be able to determine area of this square. And remember the area of a square is length times width. So our area is going to be the square root of 2x times the square root of 2x, which gives us just 2x. So now that we know the area of each cross-section, all we need to do is integrate. But before we can integrate, we have to determine our limits. Recall that we are integrating with respect to x. So in the problem, it told us that we were going from 0 to 4. And now that we have our limits of integration, we can integrate. So we go 0 to 4 of 2x dx, where this came from the area of a cross-section. So now when you integrate, you get that this is going to be x squared from 0 to 4. So you get 16 units cubed.